Hi everyone. In this video, we discuss about some of the network theorems. So we know different theorems we have like Norton's, Theorems, Superposition, maximum power transfer theorem. So all these things we discuss and we apply these theorems to DC as well as AC circuits. In this session, let us discuss about superposition theorem. What is superposition theorem? What it states? So usually we discuss the superposition theorem can be applied to a linear network, and what it says. Superposition theorem states that when any linear circuit contains two or more sources, then the response in any one element in that circuit is the algebraic sum of the responses caused by individual sources, provided when we consider only one source, then all other sources must be inactive. Inactive means all other sources must be replaced by their equivalent impedance. As we know, if it is a voltage source, it has to be replaced by a short circuit. If it is a current source, it has to be replaced by its open circuit, because the equivalent impedance of a current source is infinite, so it can be replaced with an open circuit. Equivalent impedance of a voltage source is 0, so it can be replaced by a short circuit. Now, let us verify the superposition theorem for a simple DC network. If the network consists of, here we are going to discuss about superposition theorem. As already we have stated that statement. Now let us consider one simple example. It consists of a voltage source, 3 resistors and a current source. So let us consider this is 20 volts and this is some 5 ohms, this is 10 ohms, and let us say this is 3 ohms. And here we have one current source. Its current is 5 amperes. As for the statement we have discussed, let us consider the current flowing through this 3 ohms. Now, as per the statement, current flowing through any one element is equal to the algebraic sum of currents flowing through this element caused by individual sources, that is 20 volts alone and 5 amps alone. Now let us apply this superposition theorem for this. When we apply this, first let us consider only this 20 volt source. Then we have to replace this 5 amp source with its equivalent impedance. What is the equivalent impedance of a current source? Whether it is a 5 amps, 10 amps or 20 amps, whatever it is, whose equivalent impedance is simply an open circuit. So we can open circuit the 5 amp source. Then what is the current flowing through this? Let us give I1 for this. Let us indicate that as I1 is the current flowing through 3 ohms resistor due to 20 volt source alone. Now what is the current flowing through this? As this is open, now the current flowing through this is I1 is equal to the total applied source 20 volts by these two becomes series with each other. So 5 plus 3, that is 20 by 8. That becomes, I think, 2.5 amperes. 20 by 8, that is 2.5 amperes. Now let us consider the second source alone, current source alone. Then we need to replace this voltage source by its equivalent impedance. What is the equivalent impedance of a voltage source? That we know that it is a short circuit. Simply we short this. Now let us find the current flowing through this 3 ohms resistor. Now let us represent this as I2. So this is the total current, and which is dividing into this 3 ohms resistor as well as this 5 ohms resistor. Now simple, you can apply a current division rule. What is the current flowing through this 3 ohms resistor? I2 is equal to total current into opposite resistance by total resistance. That is current division rule. Already we have solved several examples on that. So 5 into opposite resistance is 5 by the total resistance is 5 plus 3, 8. So that is 25 by 8. That becomes, I think, 3.125 amps. Now the response of a 3 ohms resistor is equal to the algebraic sum of individual responses. So that I 3 ohms is equals to I1 plus I2. 2.5 plus 3.125. It becomes 5.625 amperes. That is the total current flowing through 3 ohms resistor due to these two sources. But as per the superposition theorem, the total response by this element is the algebraic sum of individual responses, or the algebraic sum of responses caused by individual sources by considering the other source as inactive. Now, this current, or whatever the current value got, you can verify this using some other theorem or some other law, by applying some other law. Now, let us apply KCL for the given network. This is 20 volts. Let us apply KCL for this. What does KCL says? Kirchhoff's current law. What it says? It is the algebraic sum of currents at a node is equal to 0. Try to remember this current. Okay, I made sure that is 5.625 amperes we got. Now let us verify the current flowing through 3 ohms resistor using some other theorem. So as per KCL, as we know, we have to consider a node here, and at this particular node or at this particular junction, algebraic sum of currents is equal to 0. Now let us consider a node here, and this is node voltage V. Now apply KCL for this. At this node, write KCL equation. So that is V minus 20 by 5. V minus 20 by 5 plus current flowing through this is V by 3. And here in this path there is an incoming current. So that is minus 5 is equal to 0. From this, try to get V. That is, try to get V common, then we get 1 by 5 plus 1 by 3 minus 20 by 5, that is 4 minus 5 is equal to 0. Then V into, for this, find LCM, that is 3 plus 5, and try to get this to other side, that is equal to 9. So then V is equal to 135 by 8. What is its value? It may get some 16.825. Then we got voltage at this node. Now we need to find current flowing through this 3 ohms. That can be obtained by I through 3 ohms is equal to V by 3. That is 16.825 by 3 is equal to 5.625 amperes. So you compare these two. So whatever may be the theorem or whatever may be the method you may apply for this network, the response of any element should be same. So when you compare this with the superposition theorem and this KCL, in both the cases we must get the same answer. but at the same time try to observe the convenience of superposition theorem. In this, we may use only one source at a time, then the circuit complexity becomes reduced. We need not to write any equations and we need not to solve any number of equations. With a simple one equation, we can get the answer. And replace the other source with its equivalent impedance. And in the second case, we consider this source, replace this with its equivalent impedance and find the current flowing through this. Add those two. Then you will get the total response in any element. It may be a current, or sometimes we need to find the voltage across any resistor also. For that also the same process we have to apply. So in this video, we got the clear explanation about the superposition theorem and its verification. We can verify our answer using some of the theorem. Here I have applied KCL. You may apply KVL also to verify this. Okay. Thank you.